Hello students, welcome to Sri JCBM College YouTube channel, and today we are going to discuss one of the most important concept in Laplace transform, and that is the derivative of Laplace transform property. Suppose function f of t is a multiple with of a t to the power n. So n is a here positive integer, and we have two conditions for the when function or time domain function f of t is a multiple with a t to the power n, and we get the negative of 1 to the power n and derivative of with a variable s and f of s. So this is the condition for the derivative of Laplace transform. And as we know, suppose for the time domain function, if you apply the Laplace transform to the time domain function and we get in a frequency domain, and we have already discussed in previous video, we are going to discuss one of the important concept when a t to the power n is a multiple with of any time domain function, and we get the we have to apply the minus 1 over to the power n and derivative of with the nth derivative of for the f of s. F of s is nothing but the, so how we get f of s means if you apply the f of Laplace transform to the f of t, then we get f of s, and after that you are substituting f of s value and we have to differentiate that function. So n is nothing but positive integer. For n is, suppose n is negative integer, and we have to another method for that concept. So we discuss this condition or statement with the help of mathematical induction. We can prove this derivative of transformation property. So by mathematical induction, and we are familiar with mathematical induction. When you take n value is 1 step, we have 3 steps for mathematical induction. In first step we take n as a 1 and we have to substitute left hand side terms and right hand side, we get the equality, and we have to also check in second condition n is equal to m, and when you substitute n is equal to m, that also in this case also we get the equality, equal form. And another case is when n is equal to m plus 1, and for this condition also we get the equality. So this is the procedure for proving the statement of derivative of transformation. So we discuss this statement or this condition with an help of examples. Actually how it works, so I will take here one example. Find Laplace transform of examples. First one, find the Laplace transform of t square sin of 80. So this is the given condition, and look at this condition which is looking like our general statement of the derivative of transformation. Here t square is there, here t to the power n is there, n is and 2 is there, and f of t is nothing but sin of 80 is our f of t. So very simple solution. First we have to consider our f of t. F of t is nothing but sin of 80. Given, or let f of t is equal to sin of 80. And for this condition we have to apply the Laplace transform on both sides, and we get answer in frequency domain, because we have to apply the Laplace transform for the f of t and we get f of s, and that f of s we have to substitute in this case, and n value is 2. So by solving we get an answer. So here therefore apply Laplace transform on both sides and Laplace transform of sin of 80, and already we are discussed some standard rules of Laplace transform, that is sin of 80 can be written a over a square plus a square. Clear? So this is nothing but f of s. Answer is in frequency domain and we call equation number 1. Now we have to find out the Laplace transform of t square sin of 80. Now Laplace transform of t square sin of 80, just compare with the general case of the or general statement of the derivative of the transformation. So here general statement of Laplace transform is nothing but t to the power n f of t can be written. In such case we have written in the derivative form. So here n value is 2. So substitute where n is equal to 2. So minus or negative 1 square and derivative of with respect to variable s. So n value is 2. So n will be here, second derivative will be there, and f of s and f of s. Clear? So for simple simplification, by simplifying, so minus 1 square is nothing but 1 plus 1 and second derivative of f of s, then f of s is from 1. So this is our f of s, that is a over a square plus a square. And now we have to differentiate this function two times, because differentiation is second derivative is there. So second derivative can be written d of d divided by ds into d divided by ds. We can just split up second derivative as a d of d divided by ds and d divided by ds. So function f of s is nothing but a over a square plus a square. First we have to differentiate a over a square plus a square, and this one is in the form of the quotient form. So we are already familiar with the properties of differentiation, and for simplifying this one, just keep as it is d over ds and differentiate this one in a quotient rule. So in a differentiation, so denominator terms keep as it is a square plus a square, and differentiation of numerator term, that is a, and minus again. So numerator terms keep as it is and differentiate denominator terms, that is the properties of the quotient rule. So keep as it is a as numerator term and differentiation of denominator term is a square divided by a square plus a square whole square. So this is the properties of quotient for the differentiation. In next step, so d over ds is as it is. Here simplify a square plus a square, and differentiation of a terms. A is a constant, a is a constant because we are differentiating with respect to variable of s. In this term there is no s, a is a constant, then differentiation of any constant is 0, that is value of the 0. So into 0 minus a into, and now so we have to differentiate with respect to s means, so only variable we have to differentiate, s square is there. So s square differentiation of is nothing but 2 times, yes, and plus differentiation of plus differentiation of a square is a constant term, so a constant, any constant value of differentiation is 0, and divided by a square plus a square whole square. For simplification, just keep as it is d over ds, and this one is whole thing is 0. So any terms multiple with of 0, it means 0 only, and here 0 minus a into 2 times s, 2a s divided by a square plus a square whole square. So again can be written this one, d divided by ds minus 2as a square plus a square whole square. So we have to differentiate second time, because in the case here n value is 2, so we have to differentiate second time. First differentiation up to this much, and now again we have to simplify. Again we have to differentiate this case, this condition. So again apply the, because numerator terms variable is there s, and denominator terms also s is there. So in both cases it means numerator and denominators s is involved, so we have to apply the quotient rule also same. Just we have applied for here, and we have to apply again quotient rule, because we have to remove the d over ds. It means we have to differentiate the whatever the given functions. So keep as it is numerator terms as it is, that is a square plus a square whole square, and differentiation of numerator terms is minus 2as, and minus, keep as it is numerator terms as it is, that is minus of, in the case in given condition minus of minus is plus, and 2as, and differentiation of numerator terms is a square plus a square whole square, and divided by a square plus a square. So already square is there, so square into 2, 4. So this is the, just we have to apply, here I applied quotient rule property, and again by simplification, so a square plus a square whole square, and differentiation of minus 2as. So minus 2a is a constant, and differentiation of s is a, because we are differentiating with respect to variable term s, so minus 2a, and differentiation of s is a 1, so minus 2a and plus 2as. Now look at here, differentiation of a square plus a square whole square is there, so differentiation of x to the power, again we have to apply that case, that rule, and that is 2 times a square plus a square, and 2 minus 1 is 1, and again we have to differentiate a square, that is a chain rule. 2 differentiation of a square is 2s, and whole divided by a square plus a square to the power 4. And next case, in next step, so I write one more step, so minus 2a square is a square whole square plus, and look at here, 2as into 2 into 2as, it means 8 times a into a square, and remaining terms are a square plus a square, and divided by a square plus a square to the power 4. to the power 4. And now look at here, So whatever the common, we have to take common. So 2, better you take minus 2a square plus a square is a common, because here 2a is there, 8a is there, and a square plus a square also is there. Otherwise 2a square plus a square, take the common, 2a square plus a square is a common, and remaining terms you are left minus of a square plus a square, and here 4 times a square is remaining terms, and divided by a square plus a square to the power 4. So here we have to cancel here a square plus a square 4, and here a square plus a square is there, one time is there. So and this one get cancelled. So we left here, we left cube only. So again we can simplify this one, 2a time. So we are taken minus s. So 2a, and apply minus on both sides. So minus a square minus a square plus 4 times a square and divided by a square plus a square whole cube. So again by simplifying, so minus a square plus 4 times a square is there. So 2 times a plus 3a square minus a cube, not a cube, a square, and whole divided by a square plus square cube. And this is the solution for the given condition whenever f of t is t square and sine of at. So another example for derivative of transformation property. Find Laplace transform of, so t of t cube sin t, and we have to follow the same procedure, and we know that the general case for the derivative of transformation property, that is t to the power n. Just we have to compare with the general case or general statement of the derivative of transformation, that is t to the power n f of t, and we get minus 1 to the power n, value is to the power n minus or negative 1 to the power n, and differentiation of f of s. So we have to compare with this general statement of derivative, and here n value is 3, substitute t cube f of t, and before that we have to find out the f of t is nothing but sine of at, and we are already know that f of t, how to get the value of sine t. It means we have to apply the Laplace transform on both sides, and we get the solution for the sine t in the frequency domain. So after that we have to apply the f of s, that is the frequency domain, whatever we get the answer for the sine t, and that is our f of s. So that is the frequency domain form. In solution, first we have to take f of t, our f of t is sine of t, and apply the Laplace transform on both sides. Laplace transform operator L, and Laplace transform of sine t is nothing but, so coefficient of t is a 1, so 1 over a square plus 1 square, that is our f of s. This is our f of s, we call equation number 1. And now Laplace transform of t cube sin of t. Just write the general statement for the statement, and that is minus 1 over n value is cube, and differentiation of f of s in the cubic form, because n value is 3, and that is our f of s is 1 over a square plus 1, and cube third derivative of f of s. So therefore Laplace transform of t cube sin t minus, so minus 1 cube is nothing but minus 1 only, and third derivative, it means cubic derivative of f of s. Just write once again cubic form, and f of s is nothing but a square plus 1. Now simplify, so minus, and cubic derivative can be written, rewrite the d over ds into d over ds, and otherwise just write. So step by step, this is square ds square, just we have split off the differentiation condition d to ds square, and remaining d over ds, and 1 over a square plus 1. And we know that the differentiation of any terms or any conditions, and differentiate this case, and after simplifying and again apply the differentiation, and after that again differentiation. So we have to simplify up to the third derivative. So in next step, so keep minus as it is, and d2 ds square. Now differentiate this one, because we are differentiating with respect to s means, and which is again in the quotient form. So numerator terms, denominator terms keep as it is, a square plus 1, and numerator terms 1 is there, differentiation of any constant value is 0, and minus, and numerator terms keep as it is, and differentiation of a square plus 1 is, because we are differentiating with respect to variable s, it means a square differentiation is 2s, and divided by a square plus 1 whole square. Again by simplifying, minus d2 d square just by simplifying, and whole thing is 0, because any terms multiplying with value of 0, it means only 0. So minus 2s, and divided by a square plus 1 whole square. Again we have to differentiate given terms, just we have to remove the differentiation. So again can be written this one, minus d over ds into d over ds. Just split up the differentiation terms, and minus 2s divided by a square plus 1 whole square. In next step, so minus d over ds as it is, and differentiate with a variable of s. Again we get in the quotient rule, so keep as it is numerator term, denominator term as it is, a square plus 1 whole square, and differentiation of minus 2s is, so s differentiation only single term is there, so differentiation of s is 1, so we get minus 2 only, and minus, so keep as it is, numerator keep as it is, so this minus and minus 2s is plus 2 times s, and differentiation of numerator terms means a square plus 1 whole square is there, so we have to apply the basic case condition for differentiation of basic formula, that is x to the power n. It means 2 times chain rule property, so 2 times a square plus 1 to the power 1 because that value n value is reduced to the 1, and differentiation of again chain rule 2s, and numerator terms is a square plus 1 whole square is there, square already square is there, so square into 2 4. Again simplify, so minus ds d over ds, and this one is minus 2 times a square plus 1 square whole square, and here 2s into 2 2s, so plus 8 times s square plus 1 a square plus 1 to the power 4. So again we take common here, so minus ds d over ds, so what is the common here? Take the common 2 times a square plus 1, so on in the both step there is a square plus 1 and 2 is there common, so I will take here common 2 times a square plus 1 is a common, and remaining terms is here minus 2 and here plus 4 times a square, just a square, 4 times a square, because we take common here a square plus 1 is taken outside, so 4 times a square and divided by a square plus 1 to the power 4. So a square plus 1 to the power 4 is get cancelled. So in next step, so minus ds d over, and here 2 times is, so no 2 times here because so rewrite, sorry, so we left here minus of a square plus 1 because we have taken a square plus 1 is there, so another terms we left a square plus 1 plus, and simplify, so a square plus 1 whole to the power 4 is get cancelled, and remaining term minus d over ds, here what you left, 2 is left, and here apply the minus on both terms, minus a square minus 1 and plus 4 times a square and divided by a square plus 1 whole cube. So in next step we get for simplification, just simplify, so minus d over ds and remaining terms, and here minus a square plus 4 times a square is nothing but just minus it, so 3 times a square and minus 1 divided by a square plus 1 whole cube. If you take minus outside, then you would get positive d over ds 1 minus 3 times a square divided by a square plus 1 whole cube. Again we have to remove the differentiation terms again because it means we have to differentiate once again, and again this is in the quotient form, and again apply the quotient rule for the derivative, and finally we get the answer. Just write one more step. Differentiation of this term is keep as it is, numerator terms, denominator terms keep as it is, that is a square plus 1 cube, and differentiation of this term, and that is differentiation of 1 is 0 and minus 6 times s, because s square differentiation is 2s. So 3 into 2s is 6 times s and minus, so numerator terms keep as it is, that is 1 minus 3 s square, and differentiation of this one s square plus 1 whole cube is there. So by basic property of the differentiation, and that is 3 times a square plus 1, and the value of 3 is reduced to the 2. And again differentiation of chain rule, because s is a variable 2s and numerator value is, or denominator value is a square plus 1. So already cube is there, cube into 2, that is 6. First, just by simplified, and we get final answer is 24 times s into a square plus a square minus 1 and over a square plus to the power 4, and this is the final answer for the given condition of t cube sin 80. Suppose in a given example is given a hyperbolic function. In that case, we are not to refer properties of or derivative of transformation property, and just by applying the we have to convert the hyperbolic form in the exponential form, and after that that is highly convenient to solve by using the shifting property. Just we discuss one example. Suppose find the Laplace transform of, find the LT of t square or cos of hyperbolic t. So in this case again we have to compare with the statement of the derivative of transformation property, and our f of t is cos of hyperbolic t. So if you apply the Laplace transform on both sides, we get so s over a square minus 1 square, and that is the hyperbolic Laplace transform of hyperbolic of cos of 80. Also with the help of, also we can solve by another method, and we know that the exponential form of the cos of hyperbolic of any function, and that is e to the power t plus e to the power minus t and over 2, and again same, just substitute here, just I write here Laplace. Suppose we are going to find out the Laplace transform of t cube of cos hyperbolic t, and that is Laplace transform of t square, and cos of hyperbolic t can be written in the exponential form, that is e to the power t plus e to the power minus t over 2. And in this case, just take 1 over 2 take outside, Laplace transform of e to the power t into t square plus t square, or e to the power minus t into t square. If you apply the Laplace transform in both the cases or both the condition, and e to the power t f of t, we have seen in previous videos, that is when a function is multiple with of exponential of any f of t, and we have to apply the first shifting property, just we have to change s as s minus 1 or s is a s plus 1. So also we can solve same, if you take this is the Laplace transform of f of t, and we have applied previous method, just apply both are the, if you apply the both cases we get the same answer. So, but this is the highly convenient way of the solving the Laplace transform when hyperbolic functions are given. So, thank you. We will see in next video some other examples on another concept.